Hi, so as Alfred said, so my name is Charles Bussy Virat. I'm a postdoc at the University of Michigan. Yeah, thank you. But my timer is not on. Okay. Yeah, so before starting, I would like to thank the department for inviting me to give this talk, and in particular, Dolores. So I'm very excited to talk about my research that I've conducted with Professor Aaron Ridley, and I hope you'll find this presentation interesting as well. I don't know how you guys do usually, but I really don't mind if you interrupt me for questions or if you want to do it at the end. It's whatever you prefer. All right, so the outline. This talk is about space weather and collision avoidance. So first, I will give a brief background of collision avoidance. So history, what are the main challenges, and why predicting space weather matters in collision avoidance. Then I'll show how we can estimate the errors in the forecast of the solar activity. In the third section, I will speak about how we can predict the probability of collision. And then I will mix these two tools together to see how errors in the forecast of the solar activity can impact collision avoidance. And the last part, the fifth part, will be about ensemble forecasting of space weather parameters, and I'll focus on the solar wind speed. So first, a brief history of collision avoidance. So there is really only a couple of collisions so far that happened. In 2007, the Chinese destroyed one of their satellites on purpose, just to show they could do it, which created 3,000 pieces of debris. In 2009, an actual collision occurred between a Russian satellite and an American satellite, and this created 2,000 debris as well. This number of debris are only the one we can track, so they are the ones that are bigger than about 10 centimeters, so the size of a baseball. There are actually much more debris that were created during these collisions, smaller pieces of debris. And every year, the International Space Station, they perform collision avoidance maneuvers. In 2015, they actually had to perform a shelter in Soyuz. So the astronauts went into this Soyuz to get ready for a re-entry to the Earth because they just saw debris coming up, and they didn't have time to avoid it, to move the ISS. So if we look in terms of history as a number of objects, the total number of objects, the brown line, as a function of time since the first satellite in 1957, you can see a very rapid increase of the total number of objects, and particularly two strong jumps, which are the two collisions that I just mentioned in 2007 and 2009. And another way to look at the big picture of a number of objects around the Earth as a function of time is this 3D view of the objects around the Earth every 10 years. So that's basically where we are now. There is a zoom in on the low orbits and a zoom out on the right side to see higher altitude objects. So that's where we are now. Each dot is each white dot is an object. So what are the current challenges? Well, the first one is that there is a lot of objects. Yeah?
You go back to the graphs where you showed this thing. There is in the late 90s another jump. Was that
97, 97,
was
yeah.
that when the US Star Wars program shot down a satellite?
I don't know. It's possible. It's classified in the fragmentation debris. So yep, maybe. I'm not sure.
That's when they did that.
Yeah.
That was earlier.
No.
That's 78-1.
This one. That's the end of 96. I'm not sure which. For what the origin of this is. So yeah.
It was a solar satellite.
Another thing to get from this graph, I think, which is interesting, is only a very small portion of all the objects is operational satellites. So that's, to go back to the challenges slide, another one, is the first challenge is there is a lot of objects. So 25,000, 23, I think now we're more around 25,000 is really only the tractable one, so bigger than 10 centimeters. There is actually 100 million of objects which are like much smaller. And you have to think like even a very small object, it moves at very, very high speed, can create important damages to a satellite or to astronauts when they do extravehicular exits. So that's the main challenge that we have, is that the number of objects increase faster and faster. The second challenge, which is really proper to low orbit, so below 1,000 kilometers, which is the focus of my talk, is that we're not able to predict collisions very accurately. And the main reason for that is, well, the solar activity. So the drag acceleration is the main perturbing force for low Earth orbit satellites. And it's proportional to the density, as you can see in the equation of the drag acceleration. But as you know, the density is driven by the solar activity, and we cannot predict very accurately the solar activity. So that means that if you have an error in the forecast of the solar activity, it's going to translate into an error in the density and in the prediction of the trajectory of the satellite and in the probability of collision. So that's the main challenge that we have. And despite these considerations, usually when mission operators, they try to predict the risk of a collision, they assume that they know what will be the solar activity in the next few days. They assume that they know perfectly, so they make their calculation of the density and the trajectory of satellite and then the probability of collision. But of course, that's not true. And so the goal of the talk is to investigate the effects of errors in the forecast of the solar activity on the probability of collision. So to do that, there is 3 steps. The first thing that you need to do is to be able to estimate the errors in the forecast of the solar activity. Then the second step that you need to be able to do is to predict the probability of collision. And the third step is to mix these 2 tools together to predict the effect of solar activity forecast errors on the probability of collision. So it's a 3-step process. So if we go back on the first step, estimating errors in the forecast of the solar activity, the question we're trying to answer, for example, is, so imagine SWIPC, the Space Weather Prediction Center, makes a prediction of F10.7 for tomorrow. What's the probability that they make an error of +10? Okay, what's the probability that they predict 100 for F10.7, but it's actually 90? So that's the question we're trying to answer here. And we have 2 approaches that we implemented. The first one is to take an existing model, look at historical predictions, so all the predictions that it has made in the past, and compare it to observations. And like this, we have a good idea of how well it performs. A second approach is to have a model that directly provides ensemble forecasting, because ensemble forecasting allows you to get an uncertainty on your prediction. And so this part, I will talk, that's the last part of my presentation. The second big step is to be able to predict the probability of collision. So there are many ways to do that. I won't talk too much about it today, but the way we did it, we used our own tool to predict the trajectory of satellites, and then we used Monte Carlo methods to actually calculate the probability of collision. And the last step, really the question we're trying to answer, is when we try to quantify the impacts of an error in the forecast of the solar activity on the probability of collision. Taking the same example, we're trying to basically answer the question: how much this error that SWIPC makes in F10.7, how much does it affect the probability of collision? So I'll go through each of these steps, and the first one is estimating the errors in the forecast of the solar activity. So what does that mean? Well, there are many variables in solar activity, as you know. You can try to predict the IMF, the solar wind speed, solar irradiance, all the geomagnetic indices. We're only looking at 2 of them, F10.7 and AP. And there is a reason for that, is because these 2 solar parameters and geomagnetic index, they are the inputs of the MSIS model. And this is the model that we use to compute the density at the position of the satellites. So we only look at F10.7 and AP. And to model errors in the forecast of F10.7 and AP, we follow the pretty simple approach. We look at all the predictions that SWIPC made in the last 2 years, +1 day, +2 day, up to +7 day predictions. and we compare them to the actual observations. So like this, you know, well, SWIPC at +1 day, they made these errors. At +2 days, they made these errors. So we have distributions of the errors at different time horizon time. So that's what I show in these two plots. So let's look, for example, at this one, the AP. This is the distribution of the errors that SWIPC make when they forecast AP plus 2 days ahead. And this one here, F10 on the left, is for F10.7. So you can see the two distributions that are centered around 0. So in average, I made a 0 error, which shows that the model is non-biased. But we divided each distribution in 7 bins. And so how we can use this distribution of the error of the forecast of AP and F10.7? Well, let's take an example. Let's imagine that today is November 1st, 2017. You'll see why I took this date after. And that the actual value of F10.7 in 3 days on November 4 is 83. And for AP is, let's say, 9. Well, if SWIPC makes an error in the prediction of +9, meaning that they predict that F10.7 will be 92, then we know what's the likeliness of occurrence of this error. Because if we look here, a +9 error, SWIPC will make it with a probability of 8%. So there is an 8% chance that SWIPC overestimate F10.7 by +9. And we can do the same with AP. What's the likeliness that they make an error of -4 in the prediction of AP? Well, if you look -4, it is this bin, and there is a 16% chance that they make this error. So if you do that now for each value that they predict, and you add the error, you can have for F10.7 7 different scenarios. Each scenario is the center of one bin, and the same 7 scenarios for AP. Instead of only having the SWIPC prediction of F10.7 and AP, you can add their error that they might make, and you know each error, the probability that it occurs. So that's how we estimate the errors in the forecast of F10.7 and AP. You can stop me if it doesn't make sense. So that was the first step. Now the second step is to predict the probability of collision between two spacecraft.
Maybe this is a good point to pause the colloquium for just a minute so people can get their coffee. No, nobody wants coffee?
I have a question while that's happening. So error in the inputs to MSIS, estimating those. Presumably there are errors in MSIS.
Right.
If you knew those exactly, are you going to fold those into these estimates?
No, I don't. I only take the errors in the inputs, not in the actual, imagine you have F10.7 and AP exactly the right ones. As you said, there's errors after that to convert that into the density. We don't do that, but that's actually something we would like to do, and we like to use different density models to see what's the difference between two density models. If you have the exact same inputs, for example, so to get an idea of how much it changes the results to take two different density models. Yeah.
Question too. I would expect the accuracy to predict F10.7 maybe is higher at minimum than it is a maximum when you have non-transient. So
right.
The likelihood to get it wrong is probably higher.
That's also, we didn't look at that yet, because when we build this distribution, we look at 2 years of prediction, 2015 to 2017. So I guess that's almost the minimum. But the idea is to do that over 2 solar cycles and to distinguish different parts of the cycles and to make different distribution if you're at the minimum or if you're at the maximum, yeah. The reason why I did only 2 years is because I didn't find historical prediction of F10.7 and AP longer than that for up to 7 days. I know there exists up to 3 days for the last 20 years, but yeah. So that was my constraint, but yeah. Should I continue? Okay. All right. So now that we have a tool to estimate the errors in the forecast of AP and F10.7, we need a tool to predict the probability of collision between two spacecraft. So the first step, when you want to predict the probability of collision, you need to predict the trajectories of the satellites And so tools that do that are called orbit propagator. And so we build our own orbit propagator at the University of Michigan called the Spacecraft Orbital Characterization Kit, SPOC. And a very important point, when you want to predict collisions, you have to be very accurate. You have to predict your satellite trajectories, under a few meters within the next 3-5 days. And so to do that, you need to model not only the drag, but also all the other perturbing forces. And so you have to model the fact that the Earth is not a perfect sphere, so the mass is distributed not homogeneously around the globe. You have to take into account the radiation pressure from the sun, from the Earth. You have to take into account the gravitational perturbation from the moon and the sun. So all these forces are implemented in SPOC to predict the trajectory of satellites. As I said, we use MSIS in SPOC to model the density and then calculate the drag on the satellites. And so once you're able to predict the trajectory of satellites, you need to predict the probability of collision. And so for this, there are many ways to do it. What we use is Monte Carlo methods. And so the idea is when JSPOC, they tell you the position of the two objects, there is some uncertainty in the position and the velocity. So if you take one of your two objects, you don't know exactly the position and the velocity. So what we do is we assume 1,000 different objects with different position and different velocity. And we do the same for this second satellite that might collide, 1,000 with different position and velocity. And then we predict the trajectory of these 2,000 objects. And we look at how many collide. If 20 of them collide, then there is a 1% chance of collisions. That's basically a simple way to predict the probability of collision. The good thing about this is very accurate because there is no assumption. But the bad thing is computationally very heavy because you have to predict the trajectory of thousands of satellites. And in real life, it's actually more billions of satellites. So it's computationally pretty heavy. But that's how SPOC does. And so SPOC has been used in a few space missions, including the NASA CYGNSS mission. So I will talk about it very quickly. So for collision avoidance or also some other mission operations. And there is a website about SPOC if you want to have a look at it. So that was how we compute the probability of collision. So now we're going to use these two tools, probability of collision plus estimating the errors in the forecast of F10.7 and AP. We're going to mix them together to quantify the impact of errors in F10.7 and AP on the probability of collision. And so, so we just showed in a couple of slides ago a method to generate ensembles of scenario for F10.7 and AP. Remember, there were like 7 predictions for F10.7 and 7 predictions for AP. And we know the likelihood of occurrence of each scenario. They were given by the distribution function with all the colors. And if we have an F10.7 and AP, we have the density with MSIS. So we have 49 combination of F10.7 and AP, 7 times 7. So that means we have 49 different scenarios for the density, 49 possibility, different atmosphere in which the two satellites are going to orbit. That's what I show in this figure, which the only thing you need to get is that there is a lot of lines. There is 49 lines, each line is a different density at different density scenario at the position of the satellite. So all our Monte Carlo samples, so remember our 2,000 satellites, we're basically going to predict their trajectories 49 times, each time in a different atmosphere. So at the end, we have 49 values of the probability of collision. And we know that the probability of collision, I will say PC now because it's hard to say. So we know that the probability of each PC to occur is equal to the probability of the F10.7 scenario to occur times the probability of the AP scenario to occur. So we know the probability that this PC occurs. So we have 49 values and we know the likelihood of occurrence. So we can compute probability distribution function of PC. So that's what I show on the bottom left. So basically tells you, it's an example where you see that PC, the most likely will be around 10 to the minus 4, but there is some smaller values. Less likely, they probably correspond to values of F10.7 and AP that are less likely to happen. And here on the right side, it's the cumulative distribution function. So it's just an integration of the left plot. But this is really the idea of our approach, is instead of predicting one value of the probability of collision, we predict a distribution of the probability of collision. And what drives the width of this distribution is the errors in F10.7 and AP. So now I will give an example of how we applied our approach to an actual collision alert. And I will apply this to the CYGNSS satellites. So very briefly, what is the CYGNSS mission? The CYGNSS mission was launched in December 2016. It's a constellation of 8 satellites, so they orbit at 500 kilometers, so that's a low orbit. And the goal of the mission is to measure winds in cyclones. So there is the team at NASA, the CARA team, Conjunction Assessment Risk Analysis team. They are the ones who predict the collisions for all their NASA satellites, about 70 satellites. So they are the ones who make sure the CYGNSS don't collide with other objects. One thing that is important to know with the CYGNSS is they don't have any thruster. They're pretty small. They're basically my size. And so there is no thruster on them to control their trajectories. So the way we do that, the way we avoid the collision, is using drag, actually. When a CYGNSS satellite flies in the nominal configuration, there is only this part that creates drags. So it's a very small cross-section area. But when we pitch them by 80 degrees, then all the solar panels are going to face the velocity vector. So the drag is going to be increased by about 6 times. So it's going to drop the satellite in altitude, and so that's how we avoid collisions. But it's very important because, we rely on drag to do that, to avoid collision. So that means it's even more important to take into account the errors in the forecast of the solar activity. So on November 1st, 2017, we performed a differential drag maneuver. So that's the name of the maneuver to avoid the collision. To avoid the collision predicted to occur on November 5th. That's called the TCA, for time of close approach in collision avoidance. And so I basically applied our algorithm to this conjunction, basically to try to say, okay, if we're on November 1st, we want to know what the effects of the error in the forecast of the solar activity on PC. And so I basically made distribution function and cumulative distribution function of the probability of collision at different times, right before the maneuver and after the collision avoidance maneuver. Using the same method that I showed before. So let's have a look. So I basically produced this PDF and CDF. So that's right before the collision avoidance maneuver. And I like to look at the CDF. I think it's easier to see things. The first thing that you can see is that the probability of collision vary between 10 to the minus 6 and 10 to the minus 3, just because of errors in the forecast of the solar activity. So 3 orders of magnitude of uncertainty. The second thing that we see very clearly is that if you put a vertical line at 10 to the minus 4, you can see that most of the probability is on the right side. So 10 to the minus 4 is 1 chance out of 10,000 to collide. That's usually the threshold above which NASA recommends a maneuver. So if the probability of collision is more than 10 to the minus 4, then usually collision avoidance maneuvers are performed. And so what that means is that if you take this point, you transfer it here, that means that there is about 70% chance that the probability of collision is higher than 10 to the minus 4. So there is a strong chance that where the probability of collision will be above the threshold for the maneuver. If you want to know the probability that PC is under 10 to the minus 5, well, that's only a few percent. So that means that if you consider all the possible errors in the forecast of the solar activity, you still have a very good chance that the probability of collision is going to be higher than the threshold for the maneuver. So that's why we perform a maneuver on the CYGNSS satellite. And so if we look at what happened after the maneuver, so that's the same PDF and CDF after the maneuver. Well, the CDF, you can see it's switched to the left. So now most of the probability of collision is under 10 to the minus 4. There is only a 2% chance that the probability of collision is higher than 10 to the minus 4. It's mainly between 5 times 10 to the minus 6 and 5 times 10 to the minus 5. This contour plot is pretty useful. It's the contour plot of the probability of collision as a function of the error in F10.7 and AP. So what it says, basically if SWIPC doesn't make any error in their forecast, so we'll be at 0 here and 0 on AP, then the probability of collision should be something like 10 to the minus 5. The red values of PC, really the one that we're concerned about because they're above the threshold, they will happen only if SWIPC make an error in the probability of collision of plus 10, if SWIPC make an error in F10.7 of plus 10 and plus 10 in AP. So that's why it's very unlikely that this PC of 10 to the minus 4 actually occurs. So this shows that, these three plots show that the collision avoidance was effective because no matter what the error in the forecast of F10.7 and AP is, the PC dropped to values below 10 to the minus 4. But we saw before it was higher than 10 to the minus 4. Yeah.
Are the errors in the forecast of F10.7 and AP even correlated?
Yes. Yeah, that's a good question. So yeah, it can be surprising to think that the error in F10.7 is uncorrelated with the error in AP. Of course, F10.7 and AP are correlated, but not the error. So if SWIPC make an error of plus 5 in F10.7, it doesn't mean they're going to make an error of plus 5 in AP. It could be minus 10. In the paper, we actually looked at the correlation coefficient between the errors, and it's like a 0 almost. So that's actually the reason why. I'm just going to go back a couple of slides. Where is it? Yeah, this sentence, the third one, saying that the probability of PC to occur is the multiplication of the probability of F10 error to occur times AP error to occur. That's because they're uncorrelated. Otherwise, it would be more complicated. You could not just do a multiplication. Yeah. Okay, so that's basically an example of how we use our approach to an actual collision alert. And so that's the conclusion I would like to make on this part of the presentation is errors in the forecast of the solar activity are unavoidable, and they result in errors in the density and then an error in the drag force on the satellites and so on the trajectories. And we saw that it results in error of several order of magnitudes in the probability of collision. Remember, 10 to the minus 6 to 10 to the minus 3. So very large errors. And so these errors, you need to take them into account when you try to predict the probability of collision. If you estimate the solar activity forecast errors and their effects on the probability of collision, then you can allow mission operators to evaluate the true risk of the collision. Instead of only predicting one value, they have a PDF, a distribution of values. And to estimate the errors in the forecast of the solar activity, as I said, we compared historical prediction by SWIPC to observations. But there is another way we could do that, is using ensemble forecasting, is having a model, a space weather model, predicting, for example, the solar wind speed, but instead of only predicting one possible scenarios over the next 5 days, it predicts an ensemble of scenarios. Because then you can use those, as I showed, to predict an ensemble of values for the probability of collision. And so that's the last part of the presentation, is ensemble forecasting of space weather.
Before you go on,
yeah.
So is the probability of a collision taking into account what objects are being considered in that in this ensemble of 23,000 that's being tracked? Obviously, most of those are not necessarily going to be in the near orbit of the object
right.
of interest, but what are you taking into account to get that probability?
Yeah, so I think if I understand correctly, so when we do that, we only apply to two objects. These two objects are going to be our satellites, and the other object is going to be another object that JSPOC, the organism, the Joint Space Operations Center, they say, oh, this object is going to go near your orbit. So we'll only apply our algorithm to these two objects. We're not going to do it to the 25,000 object now. And so JSPOC, which is called CSPOC now, yeah, they basically track all satellites and they send to the mission operators an alert. And they're like, oh, there's this object that could enter into a collision with your satellites. And so then the mission operators, they do their calculation of the probability of collision. And then they decide if yes or no they're going to perform a maneuver, yeah. But they do that only on one object.
Thank you.
All right, so the last part of the presentation, so it's a different topic. Now we really move to predicting space weather, the solar wind speed only. But the motivation is ultimately to provide a better risk assessment of the collisions in space. So I will present the PDF model that I developed with Aaron Ridley. So it predicts the solar wind speed 5 days in advance. And it's called PDF for probability distribution function. So it relies on probability distribution function to predict the solar wind speed in the next 5 days. So PDFs, so probability distribution function, were created, and they relate the current speed, the speed now, and the slope, so the speed in the last 10 hours, to the speed in the future. So what do I mean by this? If we look at figure 13, there's 3 different distributions. So let's assume that now, right now, the A satellite tells us that the solar wind speed is 450 kilometers per second. That's the speed now. And that we see that the speed in the last 10 hours has been decreasing. Well, so what, for example, the magenta line tells you is the distribution of the speed in the next, what will be the distribution of speed an hour from now. And so how we did that is we basically took 20 years of data between 1995 and 2015, and we looked at all the times when the solar wind speed was 450 kilometers per second, and when the solar wind speed was decreasing. And then we looked at the speed 1 hour after that, 1 day after that, 5 days after that. So we got these different distribution functions. So basically the red one would tell you what will be the distribution of speeds in the next 24 hours, knowing that the current speed is 450 kilometers per second, and that the speeds are decreasing. And so from these distributions, from each of these 3 distributions, 1 hour, 10 hours, 1 day, and then we have all the way to 5 days, you can predict the solar wind speed to be either the most probable values, so the value that give the peak, but you could say, oh, it's actually, let's take the median values, or let's say the one that is at the 75 quantile or the 90% quantile. So you can basically give a distribution, an ensemble of prediction of the speed. So that's what I say on the first sentence. From this PDS, we can use the most probable value, the median or different quantiles, as the prediction of the speed in the next 5 days. So we have an ensemble of prediction, not only one value. And this ensemble of prediction, they allow forecaster to get an uncertainty on the prediction. And so that's what we show in the figure 14. So the very thick black line is the observations, and the rest are different predictions by the PDF model. The blue line is the median of all these PDFs. The light blue ones are the 25 and 75% quantile of these PDFs, and the red line, the 10 and 90. So you can see that we have an envelope which is basically different. It's an ensemble of prediction of the solar wind speed. So the PDF model uses this PDF to predict the speed, but it also uses another information, which is the solar wind speed 27 days ago. So we basically say since the sun rotates in 27 days, then our solar wind speed now should be basically the same as it was 27 days ago. Of course, the time is not necessarily 27 days. It could be 27.2, 28, 29 days. And so we basically try to find the optimum lag. To do that, we basically look at the speed in the last couple of days, and we try to match it 27 days ago, plus or minus a lag, to find exactly where we should look at 27 days ago. And then we use the speed 10 hours after that if we want to predict the speed in 10 hours. So the final prediction by the PDF model is a combination of the speed from the PDF that I just showed, and the speed from 27 days ago. It's a combination of both. So that's the basic idea of the PDF. It's a bit more complicated than that to predict. In particular, we use more complicated PDFs to predict the high-speed events, so very strong increase in the speed. But that's a basic idea. Then, if we look at the yeah.
You know, the solar wind is often discussed as a high-speed component and a slow component.
Mm-hmm.
And they have much different autocorrelation temperatures measured at the orbit of the Earth. So it would seem to affect your PDFs.
Right, yeah. So when we build this PDF, we separate fast to slow. So we basically look at, we make a PDF when the current speed is 400 kilometers per second, but then we make a different PDF if it's 800 kilometers per second. Yeah, so we have like a PDF I think it's every 10 or 20 kilometers per second from 300 to 1200 kilometers per second. So we have different distribution each time that we use, yeah. So here I show an example that using the PDF model a couple of weeks ago. So kind of similar to the example before, where the black line is the observations, so what we want to predict. Dark blue line is the median of the PDF. The light blue, this envelope, is the 2575 quantiles of the PDF, and the red is the 10 and 90. So this is a good example. That's why I show it. It's not always like this, of course, but we basically computed the normalized root mean square error, so basically the distance between the blue, the median prediction, and the observation. And we also computed the correlation between these two curves. So that gives an idea of how well the PDF predicts the solar wind speed. And so to assess the accuracy of the PDF model, we did that 50,000 times between 1995 and 2015. Because we predicted the solar wind speed 8 times a day. So we moved 3 hour by 3 hour increments. And we did that, repeated this operation from 1995 to 2015 to see how well the PDF model predicted the speed each of those times. You can do that because the PDF model is very fast to run. It's only a second to make a plot like this. It takes a second. And so it takes about, I think, like 10 hours to make this whole analysis. So that means we can assess really the accuracy of the model if we can like compare its prediction to observations so many times. So yeah, I don't show results too much about the actual accuracy of the PDF model. It's in the paper that these two references. But I do show a comparison to the WSA model, the Wang-Chili RG model. So Peter McNeice ran the WSA model for 2 years in 2008 and 2011. And we compared its accuracy to the accuracy of the PDF model. And so that's why we show in this table. You can ignore these two here, but here in 2008 and 2011 is the root mean square error of the PDF model. So if it's 80, that means that if it's 83, that means there was an error of 83 kilometers per second in the prediction of the PDF. So same in 2011, and then here you have WSA. And so one of the conclusions we had is that if you compare these two columns, is that the PDF model, the RMS error is smaller for the PDF model by about 20 kilometers per second. Another important thing when we assess the accuracy of the PDF model was to look at how able it is to predict fast transition from slow to fast solar wind. So an increase, for example, of 100 kilometers per second in 1 day. And so you're trying to catch these events, right, when the speed increases really fast. And so when you try to catch events like this, there's different ways to assess the ability of your model in doing that. And one of them is called the sensitivity. So if a peak in the speed occurs in the next 24 hours, what's the probability that the PDF model will predict it? The PPV, positive predicted value, is trying to catch the false positive, the false alarm. So if the model predicts a peak, how often will it be actually a peak? Maybe it will be a false positive that the PDF model predicts. And the NPV, negative positive value, is the negative predictive value is the opposite. If there is no peak in the next 24 hours, what's the probability that the PDF model predicts no peak? And so we looked at these three numbers for the PDF and for the WSA model. They have basically the same sensitivity, so they predict 15 to 20% of the peaks, with a slight advantage to the WSA model. But what really we can see is the PPV. So 62% for PDF, 14% for WSA. So there is a ratio about 5. So that means that the PDF models predict 5 times less false positive than the WSA model. So that's another way to compare the two models. I couldn't give much more methodology about the PDF model. I have backup slide if you're interested. But for the sake of time, yeah, didn't want to include all the methodology. But the summary of the PDF model is that it predicts the solar wind speed 5 days in advance. It produces ensemble of predictions instead of only one scenario, so it allows forecasters to have an idea on the uncertainty in the prediction. And we improved it recently to predict these transitions from slow to fast solar wind speed. And one point that I think is important about the PDF model is that it could be generalized to predict other indices, other parameters, the IMF, for example, F10.7 or AP. There is nowhere, when we made the PDF model, there is nowhere in the code where we say we use the fact that it's a speed. So we just look at numbers, basically. And we build statistics on top of that. So from these numbers. So we could easily generalize the PDF model to predict other parameters of the solar wind. And so there is a website that we made that predicts every day the solar wind speed 5 days in advance. And Peter Magnus is trying to implement it at the CCMC. And yeah, it's open source, so you can get it on GitHub.
Did you mention anything about how PDFs are related to the solar cycle?
I did not, but yes, I use this information in the PDF model. I use it here in this equation. So the first answer to the question, when we make this PDF, we took 20 years of data and we mixed everything together. We didn't separate if it's near a minimum or maximum. But we take it into account in this equation because when you're near a solar minimum, the solar wind speed 27 days ago is going to be more similar than if you are at a maximum. So the weight on B will be higher. And so, yeah, depending on where you're in the solar cycle, we put more or less weight on A and B. Yeah, these A and B are not, they change. All right, so the last slide I have is the conclusion, trying to wrap up everything. So the main thing to get from this presentation is that an accurate assessment of the risk of collisions between satellites cannot be made if we ignore the errors in the forecast of the solar activity. So that's another justification that it's important to estimate the uncertainties in the forecast of the space weather parameters. And there is two ways we try to do that. The first one was to compare historical prediction to observations. That's what we did with SWIPC, F10.7, and AP. And another way is to have a space weather model that performs ensemble forecasting. So that's what we did with the PDF model and the solar wind speed. The future work is to apply this method to more sophisticated atmospheric models. So we use MSIS. But the US Air Force, when they predict collision, they use Yakia-Bowman HAZAM 2009. But that means that you need to look at the errors in the forecast of the solar activity for more space weather parameter than just F10.7 and AP. Yakia-Bowman HAZAM 2009, I think, has something like 11 solar inputs. So you need to repeat this estimation of the errors in the forecast of all these different parameters. And so for this, again, you have two ways. Either you compare historical predictions to observations, or you extend, for example, the PDF model to ensemble forecasting of all these space weather parameters. So we are trying to look at these two different options, actually. And for the second one, I've been trying to find historical prediction of all these other solar radiance parameters. I didn't find them, so if anybody knows, I would be happy to know. But I'm also here to answer your questions. So if you have any questions, yeah, I'm happy to answer. Thank you.
We definitely have some time for questions. Stan.
I wouldn't say that Ikea-Bowman is more sophisticated. It's in some sense a lot simpler because it's just a density or density temperature. It's better tuned because Bruce Bowman went in and readjusted all, took out the bias that occurs at solar minimum and fixed a lot of problems that were in Ikea, and MSIS is to a certain extent based on Ikea. So Ikea-Bowman is a better density model, probably, but it's a pretty simple model still. And then what the HASDM thing does is, it does data assimilation, and that's Ikea-Bowman. They track certain objects and use that very high fidelity data to adjust it on the fly, which is a powerful method, and the Air Force seems happy with it. The problem I see is Ikea-Bowman, you can go get it and run it. It's papers are describing how it works, but HASDM is not. So that means that the research community and the operational community sort of parted ways, and I don't know. What the next and similarly, there doesn't seem to be a whole lot of interest on the operational side in doing anything numerical opposed to empirical. So I don't know where they want to go with all that. I just wanted to see what your comments were on that.
Yeah, thank you. Yeah, so actually, we're working with the collision avoidance team at NASA to generalize our approach from MSIS to Ikea-Bowman 2009, because that's a model that they use at the US Air Force. And so that's why I put it at the next step for us, because there is interest from the operational community. That's really the only reason for that. The fact that it's simple to use, I think it's a good thing, because we're not trying to model the thermosphere. We just want to know the density. We just want to know the one number and use it in our orbit propagator. So but that's why I say use it to more sophisticated model, was just the model that they use in operations that NASA uses.
And Sean Brunsma will tell you that both of those models are terrible, and the DTM is far superior to anything on our side of the market. And they may be right. I don't know.
Yeah, the fact that they are bad is, well, it's a problem, of course, but I think the problem, what the collision avoidance team really wants to know is how bad they are, and how bad also the density models, but also the prediction of all these solar inputs are. When they predict the DST, when they predict all these solar agents and geomagnetic indices, they don't know how much they can rely on it, and that's what they would like to know.
My opinion is that Bruce just went off the rails with these all these solar inputs. He's not getting any real benefit out of 11 different solar things. They're all highly correlated with each other, and it is true that you can do better than F-10.7, but you don't need for something as simple as that model. You don't need all that complexity, and I think all that complexity is a problem for the operational people because those not all those inputs are hardened.
Right.
You were showing how the overall cloud of space debris has risen in time. And what I would like to get at is what are principal physics mechanisms that we are looking at. Because, I mean, naively, I would assume that with the Earth's atmosphere breathing with the solar cycle, that with a strong cycle, it expands, and that overall increases the drag. And that should lead to slowly eating up on this cloud of objects. Now, you identified two single events of creation of these particles, but what is the overall source function that we are?
The overall what, sorry?
Source function of particles that we are looking at.
So let's go back to this slide. I think you were, yeah. Well, that was the very beginning. Let's see. I guess I was trying to show us. Right. So, are you asking like why the number of objects increases so fast, or?
Yeah.
Yeah. So, well, if you look at all these different categories, of course, as you said, there is these big jumps when there is a collision. But then each time they launch a satellite, there is also a debris, fragmentation of debris from the rocket bodies. And it could be anything. It could be like bolts. It could be even, how do you say that? Flake of paints. Anything that get detached during the launch will stay in orbit, not for too long, but will be will be a debris for a bit. So the rocket bodies are here. Mission-related debris, I'm not sure what it means. I know, for example, it happened that I don't know how they differentiated these two. But yeah, it could be a bolt that gets detached from a satellite in orbit. I heard that sometimes astronauts drop tools when they do extravehicular orbit exit. Some do. But other than that, yeah, it's debris from these two collisions that really made the biggest increase. Yeah, and so the reason they don't always decrease the number of debris because I think these two collisions were around 700 kilometers, so they're still there, most of them. 700 kilometers, there is almost no density, and so there is still alerts that mission operator gets with these debris at 700 kilometers.
But there must be some sort of time, e-folding time of how long particles survive
if they are in
certain orbits.
Right, if they are in low orbits. But if you have like all your satellites in geostationary orbits, when they don't use them, they either put them in the radial orbit or they stay there. But these will never re-enter the Earth. The ones that are going to re-enter the Earth in the next decades are the ones below 1,000 kilometers. But that's the only one that are re-enter, and that's decades and decades, yeah, decades and decades.
You can see, and if you look at the fragmentation debris, it's like dropping off in the last years.
Right. Yeah.
The pink or purple curve.
Yeah.
So that's exactly what you're saying. Like there's some of that debris is re-entering the atmosphere.
Yeah, but what one would like to see is
a prediction.
This kind of family of curves with altitude.
Yeah. Right, yeah.
In order to have some sort of assessment on how this is.
Yeah, that's a good point, yeah.
The other thing that Charles is not separating out there is something called fragmentation debris. Some of those are collisional debris and some of those are explosions. So we have quite a number of rocket bodies that have holdover material and holdover chemicals, and they go unstable from time to time and blow into many, many pieces.
So they're probably, yeah, in the mission-related debris, you would say, probably in this category, yeah.
And there aren't any international standards to sort of not have that happen.
Well, there are, but it's difficult to enforce.
Right.
But if you notice this source function at the bottom, the launches and the mission-related debris. You notice it was going up and it's going up, and then it sort of leveled off. And the reason it leveled off is because there were international standards adopted around that time, and you're supposed to have a re-entry plan. You're supposed to not put extra pieces into orbit like they used to, as much as you can avoid it. And the pieces, the second stages and the Marmon plans and so forth, are supposed to be deployed in such a way that they re-enter rapidly. And also the orbits between 900 and 1,000 kilometers, where space is crowded but re-entry is where a lifetime is effectively infinite, it's a bad idea to choose those altitudes for the orbits of satellites, and it's a particularly bad idea to blow things up at those altitudes,
Right.
Which has happened. I mean, as Dolores was saying, there's many types of explosions and collisions. There's inadvertent collisions and deliberate collisions.
Right.
What's happening now is the debris from the Iridium Russian derelict collision, which was what, a 600 kilometer? What's it?
I think it was 700 kilometers, yeah.
That stuff is slowly re-entering.
But yeah, on the way, it's so you have all these satellites below it. 400. You have the ISS.
Some of the earlier ones, people were demonstrating their ability to destroy satellites at 1,000 kilometers. Those have created debris clouds.
Right.
That people with us forever.
Yeah. So one of the rules I know of is to answer your question is I think now when you launch a satellite, you have to be able to somehow prove that it will re-enter the Earth in less than 25 years. That's one of the requirements. I don't really know how operationally people predict that. There is a million ways you could make these predictions, but that's kind of the rule that they have. Maybe it's the only one. Yeah.
All these CubeSats have to go to less than 600.
Yeah, the
some
CubeSats don't
number.
stay too long
And
usually.
of course, that's based on an assumption about what the sun is going to do. Which
Yeah, that's why if you
may or
want
may
to
not
prove
be
your
realistic.
set, you can just predict a higher solar activity, and all of a sudden satellites will enter 10 years before, So I don't know how they prove that very accurately, but yeah.
It used to be that every 11 years the sun would come along and clean out everything below 500 kilometers. But it hasn't done that in a while, so it's got to get on the stick.
All right. Yeah.
All right, let's thank Charles again.